What's up, friends? Instead of making this more like a class replacement, you should pause and do whatever. This is just going to be a review video where I go straight to the answers to make the video shorter and faster for everybody involved. So pause as you need it. I'm no longer going to say pause or anything like that. I'm just going to go to the answers. Um, the handshake analogy for electronegativity. What do the people represent? The people represent different atoms, or you could represent them as like the same atom, like two carbon atoms, a carbon and a sulfur atom, a carbon and a hydrogen atom. You can think of them as two different elements, think of them the same as elements. It just the handshake needs to actually represent the electronegativity. The hands in this analogy represent the electrons. That's why this atom and this atom, they each have an electron. They pair it together so that a bond forms. The strength of the handshake, like if this dude pulls hard, this dude pulling hard means a high electronegativity. The electronegativity measures how strong something wants electrons on it. And in this case, like these two dudes are like dapping each other up at the same strength. They have the same electronegativity. That's why the electrons stay right in the center. The two hands stay right in the center of them. That is what you're saying right here, the answer number 4. How do you know if two atoms will share their bonded electrons equally? Well, if the electrons stay right in the middle, then you know that the electrons are being shared equally because they're right in the middle of them. And this will happen if they have the same electronegativity, which is the measure of how strong they pull on them. Last class, we saw like lithium and fluorine bonding together. The electrons don't sit in the middle. They go closer to fluorine because it has a higher electronegativity, pulls on the electrons stronger. That's why this is right. All right, last class, we also talked about metals, semi-metals, and nonmetals. Metals are over here, nonmetals are over here. Important to know that hydrogen is special. Even though it's on the metal side, it is a non-metal atom. Going forward, we're going to eliminate semi-metals. I know you had to take notes for that, but we're not going to worry about it too much. It's kind of specific. Here's our learning goal. Today, we are going to talk about the types of bonds. So yes, we can use electronegativity to make predictions about locations of electrons in different types of bonds. We don't know about types of bonds until we talk about these: a nonpolar covalent bond, a polar covalent bond, and an ionic bond. The agenda, not relevant. Why do we care? Here are some gifts that you could look at and think about, why should I care? We got this. We got this. Wouldn't it be cool if you had some words to be able to describe what's going on in terms of science and chemistry? Our spooky spider gif. All right, folks, an exit ticket review. Trump and DeSouza. An example answer using the elements that are listed over here. Here's just an example answer. Trump is strontium, Sousa is carbon, because carbon has a higher electronegativity. DeSouza pulls on the electrons closer to him, stronger electronegativity. Which of your elements in question 1 wants bonded electrons closer to it? Carbon, I just said that, has a higher electronegativity. If you chose nitrogen and strontium, that would be nitrogen here. Swap any of the elements below, like fluorine and lithium, one F and one Li atom. This has an electronegativity of 4.0. This has an electronegativity of 1.0. The electron should be way over here. So if I were to swap out the atoms with something different, I would need to choose atoms from this list. You could choose any elements that have the same electronegativity: carbon and sulfur, carbon and carbon, sulfur and sulfur, like a sulfur here and a sulfur here, or a carbon here and a carbon here. Those would make the electrons sit right in the middle. Why? Because the electronegativities are the same. Pulling the electrons the same strength. You got a chance to copy this in notes. Notes should be over here. You need these completed in order to receive a grade. Which bond is nonpolar, which bond is polar? When they share equally, nonpolar. When they share unequally, polar. Again, which bond is nonpolar, which bond is polar? This bond is polar because oxygen pulls on the electron stronger. It is comparing 3.5 to 2.1. 2.1 is weaker than 3.5. Over here, it's nonpolar. They are pulling on the electrons in the middle the same strength. Something I want to note: elements do not have to be the exact same to form a nonpolar bond. Think about it. Carbon and sulfur are not the same element, but they pull on the electrons the same strength. Also, they don't need to be the exact same electronegativity. We're going to get into the math of that later. Nonpolar means no winner. Nobody wins the electrons here. They stay right in the middle, shared equally. Here's another definition, ionic bond. Important word, instead of sharing electrons, they're now stealing. We need to see large differences in electronegativity to do that. Draw something that would help explain an ionic bond. We got something that represented stealing. Over here, we have an ionic bond. The F atom steals the sodium atom's electron. Over here, we see the electrons are getting shared. They're getting passed back and forth. Shared. This is a covalent bond. Right here, we have a scale. So if the difference in electronegativity, delta En, is in between 0 and 0.5, that is a nonpolar covalent bond. If it's in between 0.5 and 1.7, we call that a polar covalent bond. If it's greater than 1.7, it's an ionic bond. And we'll get into some examples of that. Right here, we've got an equation. Delta En, we're subtracting the electronegativity of element 1 minus the electronegativity of element 2. It's important that you probably want to put the electronegativity of the larger one in first. So if it's like 3.0 and 1.0, you're not going to do 1.0 minus 3.0. You're going to do 3.0 minus 1.0. You want this number to always be positive or 0 if it's the same. So you always put the larger number first. Okay, using math to define bonds, I just said here, the nonpolar, it's in the 0 to 0.5 range. Polar covalent, it's in the 0.5 to 1.7 range. An ionic bond, the difference, it's not just like, hey, this one atom has an electronegativity of 4.0, therefore it's ionic. No. What if it linked up with another atom of 4.0 electronegativity? The difference between 4.0 minus 4.0, that is 0. That would be a nonpolar covalent bond. The total electronegativity can be very high. That is different than the difference of electronegativity. Here are some example calculations, like carbon bonded to hydrogen. 2.5 is carbon, hydrogen is 2.1. We subtract those, we get 0.4. Oxygen bonded to hydrogen, that's a polar covalent bond. Why? We're going to get to the why right here. Since 0.4 is between 0 and 0.5, this is a nonpolar covalent bond. Since 1.4, the difference between oxygen and hydrogen, the two elements that I'm bonding together, this is an example of a polar covalent bond. Here, an ionic bond, fluorine bonded to hydrogen. The difference in the electronegativities is high. 4.0 is much higher than 2.1. It is 1.9. The difference between them is 1.9. Therefore, since 1.9 is greater than 1.7, it's an ionic bond. There's some independent practice built into this, so you can fill out your notes here. You can go back in the video and fill out the calculations and explanations. Let me erase these now. Well, you got those if you got those. So some example answers here. You want to practice calculating the difference, telling me the type of bond, and telling me the bonded electrons. Are they shared but closer to one atom? Are they shared equally, or are they ionic bonding? Is the electron being stolen? I'm going to do some examples here. Let's put back in these examples. So how do I do these things right here? How do I get these numbers? I click on this right here and I say like, oh, okay, here's all of the elements of the periodic table and their electronegativities. So if I wanted to do zinc and copper, Zn and Cu, I would say, okay, let me go back over here. Let me say zinc, Zn is 1.6, copper is 1.9. Therefore, the difference in them is 0.3. That puts us in the range. I look up here. Oh, 0.3, that's in between these two. It's nonpolar covalent. So this gets a nonpolar covalent. And what would I say about the electrons? They are shared equally. What about chlorine and sodium? Again, if I look back on here, Na is right here, Cl is right here. That is 3.0 minus 0.9. The difference is big. 2.1 is a big difference. It's an ionic bond. The chlorine atom steals the sodium atom's electron. Here's an example of two atoms of the same type bonded together. It's a nonpolar covalent bond. They're shared equally. The electronegativity difference is 0. It's as low as it can be. Here's an example where it's like right on this borderline number, 0.5. The difference between oxygen and nitrogen is 0.5. You might say, Murray, wait, 0.5 is in both of these categories. You could say it's like, it's polar covalent, but it's kind of close to non-polar covalent. It's somewhere like in between. Yes, it's polar, but it's not that polar. And you could say like it's non-polar, but the electrons are favoring one of these atoms here. They are favoring the nitrogen atom, the 3.5. Um, sorry, oxygen. Oxygen. It's got the 3.5. They are favoring oxygen. They're closer to the oxygen atom. Don't worry about these. We'll get into those eventually. There is Kahoot, and then your 2 exit tickets here. If you weren't in class, you should draw this on a piece of paper and attach the photo to the Google Docs. If it's hard for you to insert the photo right in place, you can just attach it to the assignment. That's fine. Fine with that. Use these electronegativities to draw a bond. And by that, I mean, like, I want you to draw 2 electrons. And where are they? What type of bond is formed? Show your work. Classify the elements, these 2, as metal or non-metal. You've got a definition for those already on your sheet. Murray states that, and by that I mean the definition is like up here. And Murray states that this explain as Murray is correct or incorrect using an analogy. And by that, when I say like use an analogy here, I mean, like, use like the handshake analogy. If you were to talk about seeing a difference of electronegativity of 0.2, difference of electronegativity of 0.2, and you would say like, okay, well, if I were to explain this in terms of shaking hands, how would I explain this in terms of shaking hands? That's what I'm asking you to do there. All right, that's it, folks. Hope whatever day you're watching this, you're having a good day. Let me stop my share, wave goodbye. Bye, friends.